All right, so we're going to completely shift gears away from what you might think geometry is about for this unit. We're going to go away from shapes and angles and lines, and we're going to start talking about something called reasoning. And what this is going to lead us to is doing proofs. We'll start with talking about inductive reasoning. Just to get you thinking about what it's like, let's look at this pattern that we see here. We see January, March, May, and to determine what comes next, the best way to do it is to look at the examples that you're given and determine what's going on. So from January to March, we see that we skipped February. And then from March to May, we see that we skipped April. So we could logically conclude that we're probably going to skip June, and the next month should be July. So what we've done here is looked at the examples and made a decision about what we think is happening and put down what we think is the next element or next number or next thing in the pattern. And so we're going to say that this pattern is based on every other month. So we got another one down here to look at. We have 10, 4, -2, -8. Well, hopefully you can see that from 10 to 4 we have to subtract 6. And then from 4 to -2 we subtract 6. 2 to -8 we subtract 6. So logically you could think that, well, we're probably going to subtract 6 again. And -8 minus 6 is -14. So we've established a pattern based on the examples we were given, and we've come up with a conclusion, and we think that the pattern is that you're going to subtract 6. Okay, so those are pretty basic, pretty easy. We're going to practice a few of those also in class, but what you need to take away from this is that when several examples form a pattern, and you assume the pattern will continue, you're applying inductive reasoning. So inductive reasoning is when you use a pattern. So your formal definition, which you're responsible for knowing, inductive reasoning is the process of reasoning that a rule or a statement is true based on a pattern. That's the key to inductive reasoning. It's based on patterns. And when we have a statement or a rule that we believe to be true based on inductive reasoning, that is called a conjecture. So back up at the top, when we said that we subtract 6, or that we said it's every other month, that was our conjecture. So we're going to complete a conjecture. And this is kind of a formula on how you can do it. The product of two odd numbers is. Now the answer is even or odd. We got to figure out which one it is. So the thing you need to start with is listing examples. The product of two odd numbers. So 1 times 3. Well, that equals 3. And I'm randomly picking odd numbers. I'm not doing, there's no system here. I'm just randomly picking odd numbers. So I've picked a few, and I've noticed a pattern here. The product of two odd numbers seems to be odd. So I'm going to say that the pattern I see is that it's always odd. So my conjecture is, and this is what you're going to have to do on test, is the product of two odd numbers is odd. And that is my formal conjecture based off of the pattern I observe using inductive reasoning. So we have another one here. This one's a little different. This is more closer to what a geometry inductive reasoning problem would be. It says, write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. Well, when I look at this, I'm going to look at step 1 and see what are some examples I can come up with. So I see that there's a dot on the top and a dot on the bottom. And here there's a dot on the top, dot on the bottom, top, bottom, top, bottom. But But what I notice is on the sides, we start out with 1 on each side, then 2 on each side, 3 on each side, and then all the way up to 4 on each side. So I think that if I just put 5 on each side, and then I put 1 on the top, and 1 on the top and 1 on the bottom, then I think that continues a pattern. But I'll go ahead and look at another one just to see. I'm going to do 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1 on top, 1 on bottom. So it looks to me like either a dot is added to each side, or maybe 2 dots are added to the center, and that's what I kind of think it looks like. So 2 dots are added in the middle. So that's what I observed. So I'm going to write my conjecture, and my conjecture, I'm going to say that the pattern is formed by adding 2 dots in the middle with 1 on each side. And there's a lot of ways you could say that. This is probably not the best way to say it. I'm not an English teacher, so don't kill me on the wording. But basically, I've come up with a conjecture that I believe to be true based on a pattern I've observed. Now, when you make a conjecture and you're going to say that it's true, it's got to be true for all cases, right? So you'll see what that means as we move forwards. But what you need to focus on is that it only takes one false example to show that a conjecture is not true. So that false example is called a counterexample. An example of that would be if I said the product of 2 odd numbers is even. Well, you would say 3 times 3 is 9, and that would be a counterexample if I said the product of all odd numbers is even. So you've shown me one counterexample, you would be done. So we're going to move down and we're going to do a couple examples of some geometry, inductive reasoning. So use inductive reasoning, test each conjecture to determine whether it's true or false. If false, give a counterexample to prove it's false. So from now on, if you say something's false, you need to prove it's false. So 2 complementary angles are never congruent, true or false. Well, you need to break it down and think about it. What does it mean to be complementary? It means it adds up to 90, right? What does it mean to be congruent? Same size, same shape. Can you think of 2 angles that are complementary and are congruent? And hopefully you're thinking of 2 45-degree angles. They add up to 90 degrees. They're congruent, but we said 2 complementary angles are never congruent. So that's false because of our one counterexample. All right, next one, last one, says for every integer n. That just means we're going to think up numbers and n is going to be our variable. N to the 3rd power is positive. True or false? Well, what is an integer? An integer is all the numbers that would be on a number line. All the numbers that would be on an x-axis. Okay, it's basically your counting numbers. So let's test it out. For every integer n to the 3rd is positive. So we try with a negative number. So we're going to do n to the third, and we're going to let n equal -1. So -1 to the third, and you got to do this with the parentheses, equals -1. Well, that's not positive. So right away, that's false. Now, if we had done a positive number first, and we said n equals 1, well, 1 cubed equals 1, so that would have been good. If we would have done n equals 0, 0 cubed equals 0, is that positive or is it negative? Doesn't really matter for what we're doing because we've already proved it right here with a counterexample. So that's an example of what we're doing. So we basically try to find the pattern, say what the pattern is, and see if you can prove that the pattern is true. All right, have a good night.